Okay, we're here. Thank you everyone for waiting. I'm so sorry, it's a bit later than usual. These things happen, don't they? Sometimes things don't go quite according to plan. But thank you for watching Mr. C's Biology. Today we've got another live lesson in store for you. This time talking all about diseases and how we fight off disease, basically. Hello to Charlie and Aminous Blade and Supermaniacs, Captain Rex and Wax Llama. Hello. Welcome. Do say hi in the chat if you're there. Oh, hi Ruben as well. Hey, the OG. He's here. The man who got it all started. Great to see you. I'm very happy for you to lurk as well if you don't want to say hello to them in the chat. That is definitely allowed. But today, yeah, all about diseases. I think it's going to be a good one. But let's get cracking. As ever, what will happen is well, I'll do the lesson, and then the notes that I'm writing on, I'll put the link to them in the chat afterwards, and so you'll be able to see them, and so you can look after it, look over them as well. And then yeah, I'll also try and bookmark the video as well, so then you can see the chunks of when things are and when I talk about different stuff, so it's easy to reference as well. Hello as well, GS11 channel and Sasha. Good to see you, and Sir Buster as well. Thank you for joining me, and yeah, let's get cracking, and we'll get straight on with this. There we go. Hopefully you can see that. So this is the plan for today. A few things to tick off. We're going to talk about the body's defence systems that the body has, vaccination, and how that works. Quite a topical topic, especially in the UK and in Europe at the moment, and I guess around the world as vaccines starting to get rolled out. We'll talk about antibiotics, painkillers, what the difference is between those two things. I noticed that quite a lot of people who voted, well, a few of the first people who voted on the post that I put up did not get the question right. So we'll talk about antibiotics and how they work. We'll talk about where medicines come from in general. We'll talk about what makes the best drug. It's not what you think. And we'll talk about clinical trials as well, just to finish off, especially because that's how the vaccines have been approved. Now the drugs get approved, so that's interesting and topical too. And I've seen Carp say hello as well, so hello Carp. Right, so let's start talking about the body's defence system. So your body has loads of different systems to try and prevent disease getting into your body. They always say prevention is better than a cure, and so preventing a disease even entering your body is the best thing. Hi Louis Adolfo, good to see you. You're a regular, I know, so it's great to have you along. And so in order to protect diseases from even coming in your body or to kill them at their first line of defence, you've got lots of different strategies for that. One of the main things that you might not even think of as being a defence mechanism, but that acts as a defence mechanism very well, is your skin. And so it falls into the non-specific category because it doesn't pick out a certain virus or certain bacteria to destroy. It just blocks out anything and everything and stops it getting into your bloodstream. The fact that your skin is waterproof is a really good idea, because then things that are water droplets, travelling water droplets, can't just get in. They have to get in through your nose, through your mouth, when you breathe in or when you drink something or eat something. Although if your skin wasn't waterproof, it would be quite nice to maybe run your hands under a tap and quench your thirst. It's a bit of a weird thought, isn't it, to get water into your body? But no, it's waterproof, and that is a good thing, honest. And yeah, so the skin is the main method of defence. And we think about that. If we breach the skin, if we have a cut or an opening, and it stings, and your body tries to heal it up as quickly as possible to make sure that no disease get in, you don't get infected. Hello, Chocolate Wolfie as well. Good to see you. Now, other mechanisms that your body has to defend itself include some kind of basic things like tears that are going to wash away any bacteria that might accumulate around your eyes. Things like stomach acid. So stomach acid is really, really acidic. It's going to break down any bacteria that get in there. Sometimes, we talked about this last week, but sometimes people think that stomach acid breaks down food, but that is wrong. What it does is it kills off bacteria. It doesn't do very much of the breaking down, but it does make the conditions ready for one of the special enzymes to break down itself. What else? What other things might target specific things? Well, we've got white blood cells. White blood cells are a specific type of defense most of the time, as in they target a certain pathogen. They'll target a bacteria cell, or they might target a virus cell, and they'll break it down. They can some of them will just engulf anything that looks foreign, but some will release antibodies, and these antibodies especially will only bind to one type of pathogen. Pathogen is something that causes disease. Hello, Macbee Robinson. Good to see you. Thanks for saying hi in the chat. And so these antibodies will only bind to one thing, and that's really important. We'll talk about that a bit later in terms of vaccination. But they only bind to one thing, and they're very good at that. And they clump things together, make it easier to break down and kill it off. So that's a really helpful way that they are very specific. Some other kind of non-specific things. You've got lots of mucus around. So if you think of the mucus in your nose and your throat, that's all designed to trap different types of bacteria and things that might come in. And then you have these cilia, these little waves of hairs that just contract and flow things up. So whenever you find that you've got something in the back of your throat and you kind of end up coughing up and you see it, then that means that actually you've got a little bit of mucus in the back there, and you end up coughing up something because the cilia have wafted up some mucus that hopefully has trapped some bacteria that we didn't want into our body. Now, Ruben, if you're supposed to be in a history or maths class, then I recommend going there and catching up later. But I appreciate you sharing it with people. It's always good to have more people watching. Right, so that is body's defence in the simplest forms ticked off. These are the kind of main things that we're going to work through. Mariella, it's okay, don't worry. I don't think any of the people that I'm teaching biology to at the moment are going to get an F, if just for disliking this. But the other thing is, I don't think YouTube gives you stats on the people who dislike it or the people who like it. I think it's all anonymous. So go ahead and dislike it if you feel like you don't enjoy it. Then I won't be offended, and I won't be able to tell who it was anyway. That's okay. Let's talk about vaccination for a moment. So vaccination is where you inject something into your body that's been specially made to trigger an immune response. So it's meant to trigger something that's going to help you protect your body. And so we've got a graph here, and it's a graph with time along our x-axis. And on the y-axis, we're going to have antibody production. Because it's all about how, or maybe let's say antibody quantity. And so it's about how many antibodies there are in the blood. And if there are lots, that means your body is fighting really hard to defend against something. And if there are not many, then it means that there's not much of an immune response. It's not responding very well. So if, for example, I'll tell you what, I'll remove these two for the moment. If, for example, we have a disease that comes into our body, what will happen is our body is producing very, very little antibodies, and then it will reach the disease, and then it will start the production of antibodies, and eventually it will get to the right amount where it will be able to fight off this disease and be able to overcome it, and you'll get better again and you won't feel so ill. Whereas when we have, let's get these doses back in there. When we have a vaccine, what happens is we trigger this immune response without the disease being there. So we don't have very many antibodies, and when we hit dose 1, we first get some vaccine inside us, and it's going to start making our antibody production increase. But then over time, actually, it will decrease again, and we'll go back to almost a normal level. That's often when we'll then get a second dose of vaccine. And what will happen then is it will increase again, but this time there's a couple of key differences. It increases sharper, and it increases to a higher level, and then it will probably decrease after that. And so basically we're training our body. Once it's seen this first dose, then it's like, oh, okay, I kind of know how to make this antibody. I know how to produce it. You see the second dose, and it's like, oh yeah, I've done this before. Easy. I'll do it again, but better. And so it does it faster. It does it to a higher level, and it's more effective. Because then when the disease comes along, it's had some practice attempts, the body knows how to make this antibody. It's not going to sit around and be like, oh, what's this disease thing? It recognises the disease because it's got similar parts to it that the dosage has from the vaccine. And so this time it can have exactly the same response. In fact, I'm going to make it steeper even. It's steeper, it's higher, it's able to fight off this disease, and then actually the disease is gone and you're okay and you can get on with your life and you don't feel ill for very long. And so when these vaccines for coronavirus are coming about, what's happening is you're getting a jab that's going to give you an opportunity to respond to the coronavirus vaccine without having the coronavirus virus without having to have the virus itself. And then when the virus comes along, it's not going to mean that you won't get unwell, but it will just minimise the chance of it being serious, because actually your body can respond to it so much quicker and so much more effectively because it's had these kind of trial runs where it knows how to produce these antibodies already. Now, the way that works is actually that it has some cells, a special type of white blood cell, which is a memory cell that sticks around. So after dose 1, the body has worked out which cells are the right ones to make the antibodies, and they start making the antibodies as quickly as they can. And then actually after that, they think, oh, okay, well, we'll save some of these memory cells that know how to make this antibody for later, in case it ever comes back again. And they do that actually normally for any disease. They'll try and learn how to deal with it and then hang on to that knowledge. Same way why you tend not to get chickenpox more than once, because once you've had it, your body learns how to deal with it, and it's not going to have to deal with it again. And if it does come along, then it knows how to deal with it, and it can just kick it out. And so this is just doing the same thing, but trying to work it out. Great, Ruben's got to go. That's fine. I don't mind if you have to pop in and out. But I'm glad that you're still watching. I've still got 12 people watching, which is fantastic. So thank you. Anyway, let's move on and talk about antibodies. And so, not antibodies, antibiotics. And that's the tricky thing with this. They all sound the same. But antibiotics, anti in this case is meaning against, and biotics meaning against a living thing. So it's not against a pathogen like a virus that's not living, and it's not an antifungal or an anti-malarial targeting a specific one. So if you've seen the poll that's open on my channel as well, then it is an antibiotic that fights against bacteria. Okay, so you can go vote there and be correct and be smug amongst all your friends. But let's talk about how it really works, and we'll talk about antibiotic resistance. So an antibiotic, targets a part of a bacterial cell that a human cell or a plant cell doesn't have, and that is the cell wall that's made of chitin. And so if it targets the cell wall that's made of chitin, there's no chitin in our body that we need, and so it can stop the production of the bacterial cell walls, and then these bacteria can just break down, and they can't build, they can't work themselves out, and so they die. Whereas the danger here, though, is if we use antibiotics too much and if we don't use them properly. So a doctor will always say, take these antibiotics for this bacterial disease. You don't need them for a flu or for a cold. You might feel grim and you might think that it would be a nice idea to have some medicines to cheer you up, but it's not going to actually help. But if you've taken them for bacterial disease, they will say, complete the course. Have the full set of antibiotics. Don't just take a few, feel better, and then don't take any more. It's always best to complete the course. And so let me explain why that's really important and why that prevents us from having antibiotic resistance. So imagine this is my group of bacteria that I've got here, and I take my antibiotics, and after a few days, actually it's killed off a few of my bacteria. Happy days, one of them's half there. After a couple more days, it kills off another bunch. Oops. There we go. And so after about a week, I'm feeling a bit better. I'll be all right soon. And then actually, even better after that, I'll feel even better than that. And so I've only got a few left. But what I didn't mention is that these green ones that I've drawn are actually the antibiotic resistant ones. Okay, so they're harder to kill than any others. So if I kill off a few, and suddenly I'm feeling a bit better, suddenly these ones that are sticking around, they have an advantage. They're more likely to be able to survive, they're more likely to be able to pass on. And now where there were just 2 and about 20, I didn't actually count, there are now 2 and 5, so 40% of the bacteria are now resistant types. And if we imagine that these ones are now the ones that are going to grow and reproduce, well actually I've got I've got more of the green ones, more of the more dangerous ones than I had before. And if I carry on using my antibiotics after that, so I've stopped for a little bit and then I go back to have some more, then actually it will kill off the blue ones first because they're the weakest, and the green ones will stay. And if I then actually stop again and think, oh, well, I'm getting better, then again the proportion of the green ones that are the stronger ones are going to stick around for longer and longer and longer. So we're going to end up harvesting a stronger population of bacteria. Now the way that this works is just really simple natural selection. We're putting in a selection pressure and saying, can you survive this? Can you survive this antibiotic? And actually, if I continue to use my antibiotics all the way to the end, then the likelihood is there'll only be a couple left and our body can sweep them up. But if I use it and then I feel better and then I stop, then these bacteria have a chance to reproduce, and then actually the bacterial infection can come back even worse. Hi, Juan, good to see you. So yeah, that's why it's really important to make sure that we're cutting down on just using antibiotics for everything, and creating a selection pressure that then means that these bacteria have a chance to grow and even more and to multiply when they are antibiotic resistant. And also we need to stop just using half a course of antibiotics and keep on using them all the way to the end. So we're not creating these superbugs, these antibiotics that are resistant, that aren't able to be able to fight off, that we can't fight off with any normal disease, any normal antibiotic for the disease. All right, so we've talked about the body's defense, we've talked about vaccination, and we've talked about antibiotics. So we're making good progress, just a few more things to work through. Let's talk about painkillers. So the common question with painkillers is, can they actually cure disease? And the answer is no. They definitely can't. What they do is they treat a symptom of the disease. And so this is something that if you're studying GCSEs, you'll need to know that a painkiller is sometimes referred to as an analgesic. And that just means it's a painkiller. It removes pain and it treats a symptom of a disease. It doesn't actually end up curing the disease at all. If I've got a headache and that headache is being caused by a flu that I've got, maybe a temperature, I can treat that pain, I can treat that uncomfortableness with a painkiller, but I can't actually get rid of the flu with just a painkiller, with some paracetamol or some ibuprofen. That's not going to do any good for me. But you might be thinking, well, hang on, we talked about antibiotics, we talked about painkillers. Well, where do these drugs come from in the first place? Well, it's a really good question, and the answer is basically plants. They come from lots of different places, but other organisms is basically where we harvest them from. So I've got a drawing that I did of foxglove, and I've got a picture of a willow tree because I had tried to draw a willow tree and it didn't look very good at all. But this is a foxglove up here, and so foxgloves, we found out in the last kind of century or so that foxgloves have a chemical inside them that we can use as a heart medicine, which is something called digitalis, and it slows down your heart. So it's quite a good treatment for some heart disease, and so it is something that is synthesized and turned into a chemical called digoxin. That's often the drug's name. And so there are types of digoxin that you can get, your doctor might give you, because it's come from a foxglove, that they've just synthesized this little chemical inside the whole plant. It's not the whole plant, it's just one tiny bit of it, and they've made it work. Another example is the willow tree, where we've got aspirin from willow. And the amazing thing about aspirin is that people, even before they knew that this was the chemical that was active inside it, people would chew willow bark in order to relieve themselves of pain. So we can look back at some of the earliest records of medicine and of people using things to treat pain, and people are chewing willow bark in kind of the ancient times, because it's something that ends up relieving pain and reducing stress. And so they chew on this willow bark, maybe while an operation is happening on the lower half of their body. They're chewing away furiously to try and relieve some of the pain of that. One other thing that is actually slightly more effective is chewing on a beaver's tail, and the reason for that is actually that beavers eat willow bark, and as they eat it and digest it, they store the chemical, the active ingredient that actually makes the aspirin, in their tail. And so we can actually harness that by chewing on a beaver's tail, which is even more bizarre. But thankfully now what we've been able to do is we can synthesize, create chemically the aspirin chemical from some willow bark and from some other things. Another really important discovery of medicines came from a mould, and so you've probably heard of someone called Alexander Fleming. And so what he did is he had a tray of mould that he was growing, and he quite liked looking at the mould and realised that something. No, he was looking at a bacteria. Sorry, he was looking at some bacteria called Staphylococcus aureus, and he realised that actually these bacteria had been killed by a mould, and he was really annoyed. And but wrote it down and made records of it. And then a few years later, we were looking at things that we needed to kill bacterial infections. And some people called Florey, Chain, and Heatley, they came across his work and managed to synthesize penicillin, and it fights bacteria infections and is one of our first antibiotics. And because it was World War II, the Americans worked with the British in Oxford to make this penicillin come to life and save lots of lives when people had lots of infections. Hi, Amanus Blade as well. Good to see you. Glad to have you with us. Right, next thing, and we're on to our last couple of things, and then we'll wrap it up for today. But the best drug, and it's not what you think. What I'm talking about here is the best. What makes the best medicine? What are the characteristics of a good medicine? And there are a few things. Obviously, we want a medicine that is safe. Okay, and so when you think of the packets that you get, the kind of leaflets that you get in a packet of paracetamol, and it has a list of all these different side effects that you might possibly get. And obviously, most of the time, you don't get any of those side effects, but they have to write them down just in case. But we want to make sure that these medicines actually have side effects as little as possible, and we want to make sure that actually they're not going to cause any damage to our body. There's an awful story of a drug called thalidomide that didn't go through the proper checks, or there weren't proper checks in place when it was first created. And it was designed to give to mothers, and they would take it and it would relieve morning sickness, which is the illness that you get when you're pregnant. And so they take this drug and it worked really well at being able to prevent them from being sick in the mornings whilst they're pregnant. However, when the drug got processed in the body, it turned into a dangerous form that was the same kind of thalidomide substance, and it ended up causing the babies that were inside the pregnant mothers to have deformed limbs. And so some of them didn't have limbs, some of them had shorter limbs than they should normally have. And so that was a drug that actually wasn't safe. It was effective though. It did do the thing that it was supposed to do, but it wasn't safe. And so we can't compromise on safety if it is effective. But the effectiveness is the other thing. We sometimes call it efficacy, and so that's about keeping it as effective as possible. It's all right to have a safe drug, but if it doesn't do what it's meant to do, then it's no use at all. If you take a paracetamol and it's not got any side effects at all, but it doesn't actually help you with your headache, or it doesn't actually help you with any pain, well, that's not very effective. So there needs to be balance of safe and effective. We also need to think about how does it get into the body, and how does it get out of the body. Let's say the body. That's really important too. We want it to be able to survive and be able to get in without getting broken down. So some drugs, if you think of insulin, so people who are diabetic and might take insulin, they can't take a pill of insulin because that would be swallowed, it would go into the stomach where there are protease enzymes that break down proteins. If you're not sure about that, it was on last lesson, so check out last week's video. And so it gets broken down by the protease in the stomach and never gets to the blood. And so instead, if you want some insulin in your body, then you have to inject it. And so you get an insulin injector. Hi Krishna, great to see you joining us as well. Thank you so much for listening, guys, and thank you so much for being here. And so those are kind of few things that we need to really check when we are thinking about a drug, and making sure that all those things work together in order to make sure that we have everything that we need to make this drug safe and effective, and make sure it can get into the body and get out of the body. We might also be able to work out what the dosage is. That's something that we'll work out on a clinical trial. Now, let's just tick off a few things. We talked about painkillers and analgesics, as they're called, and how they cure just the symptoms. They don't cure the disease itself. We talked about where medicines come from, mainly plants, sometimes molds, and actually even more so, people have been looking at using things like plants in order to, plants in kind of crazy places like in the rainforest to try and extract tiny things from them. Insects, sometimes we're trying to find some drugs from them, because these are things that actually have survived against antibiotics and disease themselves, and so we need to see what we can do. Hi Dark Prince, good to see you all the way from Lebanon. Thank you so much for tuning in. It's good to have viewers all around the world. It's not normally what I have in my lessons. And we've just finished talking about the best drug. If you missed it, feel free to scroll back and watch and catch up. We're going to talk about clinical trials just to finish off, and then we'll go from there. So clinical trials are the trials that we test drugs on to be able to make sure that we end up with something that is safe, effective, and can get out of the body in the right way. So the first stage of clinical trial is actually a preclinical trial, and that is where we test it on tissues. And what we mean by that is not a handkerchief, but a group of cells. And so we'll just test this drug on this group of cells. It might be the group of cells that are meant to be targeting. If it's a drug that's meant to act on muscles, then we'll take some muscle cells and see, does it work? Does it do the thing it should do on just a collection of cells outside the body? We might then test it on some animals as well, just because we want to check that it works before we put it in humans. In the scientific world, animal lives are accounted a little bit less than human lives. That's a debate for another day. But they test it on animals to make sure that when it comes to testing on humans, there's not anything completely unexpected that comes out. Now, after that, we test it on healthy individuals. You might be thinking, hang on, this is a drug that's hopefully going to cure some sick people. Why are we testing it on healthy people? Well, actually, before we get to testing it on sick people, we just want to check, are there any horrendous side effects? If you test it on a healthy person, they're fit and well, they're likely to recover from some minor side effects, and they might be in a better state to be able to determine what are the side effects of this drug, because they're not having to work out what's the pain from my illness and what's the pain from this drug side effect. And so it's good to test it on them first. And they are often young, healthy people, and they'll give a very, very small amount. So it's not aiming to actually try and cure a disease. You wouldn't try and give someone a treatment if they're not ill, but you give them a very, very small amount that hopefully won't have any negative side effects, and will hopefully assess, is this drug safe or not? The next step, it's also worth pointing out, these people are volunteers, and you can volunteer for this online. You can sign up for different clinical trials. And it's an amazing thing to do. It can be a bit scary, thinking actually, I'm going to get a drug that no one else has before. But they do pay you, they can pay you quite well to be ill or to be given a drug for a bit and to see what happens. And this is obviously what happened with the Oxford vaccine trial and with other vaccine trials around the world for the coronavirus vaccine. They asked for healthy people to volunteer to see, actually, does it work? And then after that, after they test it on healthy people, they then test it on the sick people. And this is now saying, actually, is it not just safe, but is it effective? Does it do what we want it to do? Does it do what it says on the tin? And so this is where we're actually looking for an effect. We're looking for these sick people to start feeling a bit better. It might be, if it's a cancer drug, we're looking for the cancer to diminish, the cancer to be gone. And if it works, then amazing, it's great. If it works to some extent, then that might still be worth putting forward and getting approved, because it might be something that can just add to the repertoire that these doctors have, their arsenal for dealing with all sorts of diseases. So it can be a good thing, even if it's not perfect, if it's not 100% as good as you think it might be. And then you get an approval from the government to say that it is safe. And so that's the Food and Drugs Administration in the United States. And there are different governing bodies across the world that will say, this is a good drug, this is a drug that doctors can prescribe. And if they say that, then that's great, you can start selling it, you can start giving it to doctors. But there's always a phase 4, a kind of end stage, where we're continuing to look at the drug, continuing to check, is it still doing what it says on the tin? Is it still safe? Are there loads of side effects that are being reported? Are doctors actually using it because it's a better alternative, or is it actually not worth it? Drugs cost millions of pounds to make, millions of dollars to make if you're American, and in order to get it through to the stage of approval, there's been loads of time and money invested into it to make sure it's going to work. So it kind of had better work, or they'll make a way to make it work because they've invested so much into this. And it's worth saying that there's another type, as part of these trials, there's a type of trial called a double-blind trial. And so double-blind doesn't mean that they're using blind people, but it just means that two people don't know what's going on. So you can imagine you've got a scientist, and they are giving these doctors some drugs that they're giving to a patient. And so the doctors who are administering these drugs don't know whether they're giving this person the real drug or whether they're giving them a placebo, just a sugar pill, something that they're testing against as a control test. And so doctor doesn't know and the patient doesn't know. Only the scientist back in the lab has a list and has the numbers that kind of match up to work out who's got which one. The reason for that is then it's not that, oh yes, you've got the drug, this one should work, and then someone takes the drug, oh, and they feel like it works because of the psychological effect of knowing that they've got a real medicine. Or it might be, well, you've just got a placebo, a control pill, it shouldn't work, but we're just checking and seeing if the drug really has an effect in comparison to this. And then because they know that, psychologically, it doesn't really work. And so this is just a way that they get it to be able to check that the drug definitely has an effect. And the placebo is a really useful thing because there is such a thing as a placebo effect. If you've got a bit of a headache or something like that and you take a pill, whatever that pill is, even if it's got nothing in it at all, it might still make you feel better. Because the placebo effect thinks, oh, I've taken a medicine, therefore I will feel better. Hello from the Ukraine. I'm afraid I can't probably pronounce your name, but I'm so glad that you're watching as well. It's good to have viewers from all over the world. I really appreciate it. Thank you so much. We're actually just coming to the end there, so the placebo was kind of the final point that I was going to talk about. And so that is clinical trials that we just ticked off as well. And so we talked about the body's defense, specific and non-specific things, vaccination, how each dose changes the body's antibodies and enables you to be better prepared for when the real disease comes along. We talked about antibiotics and how they kill off bacteria. Go and vote in my poll if you haven't already to let everyone know that you know the correct answer. Painkillers don't treat symptoms, don't treat the disease, they only treat the symptoms of pain. They can only get rid of that, they can't cure it properly. Where do medicines come from? Mainly plants, but sometimes mould, and we're looking at some other plants and insects. The best drug must be safe and effective and be able to get into the body and out of the body in a good way. And clinical trials, we test on tissues first, and we test on, and then we test on healthy people, then sick people, then we get approved. So I've just had a comment from Sad Potato. So you say that a fake pill can theoretically make a sad potato a happy potato. Well, the thing is, these drugs, they work up to an extent, of course. The placebo effect, if you break your leg and you think, oh, I know, maybe this pill, if I believe this pill will fix my leg, then it will work. You take the pill, I'm afraid your leg's still going to be broken. You should get medical advice and go to hospital. But if you're taking a placebo in this clinical setting, or if you just feel like it's going to be a good idea to see if it will do something, then do try it out. Do some more research on the placebo effect. It's absolutely amazing. I read something over Christmas about how even just thinking about the placebo effect had an effect on some people, and so they felt pain less because they'd talked about it, even knowing it was placebo was better. So there are some crazy things that your body just does because psychologically it kind of works. So your body thinks, oh, this should happen, and therefore it perceives it to happen. So your body is an amazing thing. It's pretty impressive. I'm going to call it a day there, and I hope you found that really helpful. I really appreciate everyone watching and tuning in. If you want to add any more questions in the comments, I'm really happy to answer them later. I'll type out some answers to you. As I said at the start, I'll put the notes that I've written up here on a PDF and put that on the YouTube description. Someone's had too much online lessons. Hopefully that's been great. If you have found it helpful, then you're welcome to consider supporting my channel. Buy me a coffee, but you don't have to. I'm just glad that you're here, glad that you're learning. That's the most important thing. So thank you very much. We'll be back next week, hopefully at our usual time, depending on how all things go. It's just how it is. But yeah, thanks for watching, and I'll see you later. Bye.